So hi, Orizaki, I'm co-founder and CEO at Bioraptor. I come from a software engineering background, spanning domains ranging from cybersecurity, healthcare, biology. And in the past 4 years, we built Bioraptor with a goal of making AI more accessible to bioprocess and driving data-driven bioprocess. And we'll dive into more of the learnings, both from Bioraptor and in general from tackling AI and software initiatives in other industries because they relate also to this topic. So let's dive in. So the agenda for today, we're going to talk a little bit about the AI expectations versus reality. Then what data we need to have as a backbone for trusted AI, what it actually means to have usable AI, and the steps we can take to implement, reduce risk, and have a higher probability of success with our project. So, and then we'll open to Q&A. Feel free to dive in at any point in this talk with questions, and we'll answer them either during the talk or at the end. So first of all, we'll start with discussing what we want to achieve. So ideally, we'd have a ChatGPT-like experience with bioprocessing, so we could get answers to all of our bioprocessing and biology-related questions at either by voice or by just texting it. So at this point, I think it's everyone has had experience with tools like ChatGPT or others. There's quite a lot in each and every aspect of our lives, from handling our meetings at work to just getting a recipe from what we have in our fridge. And why these tools are so effective? It's first of all, there's no learning curve. We just are able to use them. It's just using natural language, either speaking to them or typing in as we would speak to a colleague or any human interaction. That ease of use makes it very easy to dive into it and use. The second, and the reason that they work so well, is that they didn't appear magically. We've probably all started using them around the last 2-3 years, but the journey in order to get to the point where we have ChatGPT as it is today started off over 25 years ago with the digitization of vast amounts of text. So first of all, digitizing all the books on the planet. And later on, we also got Wikipedia. We have online forums, Reddit, X, or Twitter. So all these interactions that are publicly available have allowed us to train models on huge data sets of text. And as we're seeing the models evolving more and more, also huge data sets of video, of online images that are also tagged and usable for AI. Another thing that we have is, since we have billions of user interactions with these models, we constantly get a reinforcement learning for them. So every time you interact with a model, even if you don't give explicit feedback, like the thumbs up, thumbs down that it sometimes asks you, or which of these two answers do you like, even without that explicit feedback, you're also giving it feedback. So even when you say, this isn't what I asked for, and asking for clarification, the model can learn from that and understand, so this was not a good answer, I need to improve. This is actually what he meant. And that's what will drive that model to learn more for the next iterations, the next versions. So all these interactions also provide training for the model. And that drives us to the next question. Why don't we have BioChat in ChatGPT? Why why can I use it for getting recipes, but I can't use it to get good answers on my bioprocessing data? So the first answer is there's no structured, standardized bioprocess database that's publicly available. So when we're looking at bioprocess data, it's a lot of silo data that's living in online and real-time systems like the bioreactors, sensors, the downstream equipment, filtration equipment. It all has machine-generated data. Then we have a lot of human data that's generated in lab notebooks, which are either electronic or pen and paper notebooks that are just on someone's desk or in someone's drawers. We have post-it notes around the lab on screens in the lab, also noting things that happened, and a lot of context that's carried in each and every scientist's head from their day-to-day experiences. So that data does not reside in a machine-readable format that can be used. In addition, we have all the at-line, offline data, organism metadata. So a wide variety of data modalities, so ranging from time series data, observational data, subjective measurements, and all that data doesn't have a clear, contextualized, and harmonized way to document it. So that drives us to what do we mean by context and why context is important. So if we have a piece of data without context, like in this example, it can be two very, very different things depending on the context. And it applies also to bioprocessing. So if we have a piece of data in our upstream process that, for example, we're measuring yield in upstream, and we're just doing a local optimization for yield in our upstream process, and that's our only target function. And also in our downstream process, we're also optimizing for efficiency. One of the things that can happen driving for those local optimums is that we optimize the downstream process and we optimize the upstream process independently, getting more yield in upstream, but actually adding some contaminants that are harder to filter in downstream. And then the overall efficiency of the process is actually going down. So without contextualizing and having that cross-unit visibility, that's something that's key and important to keep and document. So understanding in downstream which upstream process it came from and what are the parameters that affected the lower efficacy in downstream. And the next question that always comes up with AI and in general in data-driven systems is how much data do I need? And there's it's a much more complex question than just how much data do I need, because first of all, you need to ask, what do I need the data for? What am I trying to achieve? So I'll give an example of a very shallow data set that provided the value because the question that was asked resided in that data set. So we had a customer with a handful of runs, and they were having batch-to-batch variability in those runs, and some of the batches had very low performance. Within those runs was enough data to understand what was driving those low-performing runs. In that case, it was something to do with the oxygen feed. But the data resided in those 6 runs, so I didn't need more data than those 6 runs to answer that question. On the other hand, if I wanted to ask a more complex question and I wanted to have a digital twin model for that organism in a much more varied environment and how would different interactions between different parameters would affect that process, I would need more experiments with variability within those data points. So I would need a little bit more exploratory experiments to be able to map out that design space. So I'm going to give another example here. We're going to walk through it step by step and showing how context and adding more data to that context allows us to give an understanding, and then we'll tie it into how AI can assist us with this. So first of all, I'm going to do this manual approach of we're starting off with a process where we only have the measured yield per run. So I only have a list of my runs and what yields I got. So what do I know from this? What can I understand from that data set is a third of my experiments nor runs got a high yield, and 2/3 have a low yield. But I can't understand anything that's more complex from that. When I tie into the online sensors into those yields, now I have correlations between different parameters like pH and temperature. And I know, and I can understand now that pH and temperature at specific areas positively affect yield within those groups. But this still, in this case, I still didn't get an understanding what's driving that from the low performing runs to the high performing runs. I can improve within the group, but couldn't get the understanding what's differentiating between those high and low yield runs. Add another set of data into the context. So if I add now my seed train data and understand what seed train and how I ran it to the online sensors and the yield, I can now understand and see patterns like that when thawing the initial seed culture for 2 hours versus 3 hours really has an impact on my ultimate yield in the process. So I can now see that variability has enough data within existing experiments. I didn't need to do a new design of experiments campaign. I have variability in my experiments. In this example, it's because of just different people doing different workflows. So one person, first of all, takes something out of the freezer and then does a step, and the second maybe takes the batch out of the freezer and then goes to get coffee. So that small variability in how people work also drives understanding and data. The next step, I'll add my strain data. Now I can understand which genetic modifications and different strains drive robustness to pH and temperature variations. So I can still get more and more and better understanding of my organism. And in our last phase, let's add our media data. So we now have media data and metadata. And in this case, we finally got an understanding of what's differentiating our high and low yield runs. So in this case, it was the correlation between media freshness. So understanding that the same media batch that was opened and used fresh versus after 2 weeks afterward was opened and stored in a refrigerator had a dramatic increase or decrease in this case on yield and the performance of the organism. So that process, as I showed it now, we did an iterative process where we added piece by piece. And that drives us to what can AI help us with in this case. So a computer system can take all of this data without bias, without me having to hypothesize, wait, is it something in the seed train? Is it something in the strains? Is it something in the media? And just have an open-ended question of, this is my yield. I want to understand why these are higher performing and these are low performing. And then it will get us all these correlations and can rank them by how strong these correlations are. So give us the highest impact. In this case, it was the media freshness, and then the less impactful ones as a secondary. So that's the AI capabilities. Another question that's very important to ask, and it ties into how to manage a project, and we'll also expand on this later, is what aren't I tracking? What should I be tracking? Now, I'll start from the end. Maybe we'll never be able to track everything, right? Because it's always you don't know what you don't know. So I'll give an example of a process and demonstrate how an analysis can show us without tracking something the clues to what we should be tracking, and then how we added that tracking. So let's start with what the process is. It's a multi-stage process with batch-to-batch variability. Sure, you all it will resonate probably with most of the people in this audience. The same strain, same process parameters that have been running for years, and yet different outcomes between batches. So, as they say, that's biology. You never know what you're going to get. But in this case, we can show how we can get the clues and then understand what's driving that variability. So we'll start with the available data at the initial stage of analysis. So in this case, there were no online temperature sensors in all the stages. It was manual temperature readings at specific parts in the process, and only for specific areas. So there's no tracking of ambient temperature, of water intake temperature, thaw times and temperature of the cultures. And then we dive into the existing data. So diving into and doing an analysis now of the existing data, the AI found that there's a few things that are interesting and correlating with those variabilities. One is temperature variabilities do show that they impact both the yield and the quality of the organism. Two, we show that the date had also very, very interesting correlation with the outcomes, which gave a good clue that it had something to do with temperature and something to do with temperature and date, which led to let's start investigating deeper and add more temperature measurements at more time points and more areas. And in this case, as I said, there's no ambient, no intake temperature. So we started taking additional areas. And then the understanding was that if it's seasonal impacts, then it's probably either in ambient or intake temperatures. And in this case, it was very clearly that it was intake temperatures, which have a very, very, very big difference if you're not controlling them between summer and winter. And that was indeed the case in this case. And it drove two things. One, the process was drastically improved, so over a 2x improvement in yield by just controlling that, and also process stability. And two, that understanding that the temperature is a key parameter in this process. Adding online sensors for intake temperature and ambient temperatures was something that became a no-brainer to add that because it provided such a high value. Now we'll start talking about implementation and steps for implementation of AI. We touched on what we can get from AI, how it can help us. And now we'll talk about how to implement and some of the pitfalls in implementation. So first of all, I'll lead with two examples on how to drive adoption and what drove adoption in this case. So two things that we all use in our day-to-day, probably used several times just today. One, GPS. So GPS has been around for over 50 years, and yet it's become more commonly used in every household in the past probably 25 years or so. And what drove that change is that GPS, when it was used by military and niche applications, was usually you got a readout of coordinates. And only when we got a good user interface, so when we got the ability to overlay our location on a moving map, in a car, that actually drove that it became something that we use in our day-to-day. And the second example is voice assistants like Siri and Alexa. So we started off in also it's a technology, the pieces of it have been around for over 20 years, 25 years. And we all had voice activation for phones about 25 years ago, but we needed to have a very, very clear understanding of what we needed. So it wasn't very accessible. I needed to know exact keywords that I could use and get. So, for example, to dial, I could say and just read the numbers, but I couldn't just tell it call mother or call someone at the office. And as it improved, became more and more natural experience. Today, everyone, there's no learning curve, as we said. Our parents and grandparents can use the technology without any training. So that's what drove and drives it. And that's also a key thing for adoption in organizations. So in order to get good adoption in any tool, it needs to be easy to use and provide value in the day-to-day. So whether it's how you're documenting data, how you're getting it to work, it needs to be something that's providing value in the day-to-day experience of who's documenting. So I said for ChatGPT-like experience, the ability to ask questions easily and get complex correlations from a broad data set quickly. That's something that's a goal. We need to have traceability. So if we don't trust the answers that we get, then we won't get adoption. So every answer should be linked back to the raw data. So that you don't have hallucinations. So if you've used the ChatGPT for bio, then you know that it sometimes gives you papers that don't exist or results that don't make sense. If we ground the truth with real data that we have in our organization or link to a real paper, then we have that trust and we can move forward. And lastly, keep a human in the loop. So we're use it as a co-pilot first. The AI retrieves, drafts, does the heavy lifting and all the grunt work, and then still have a human verify it and make sure that it makes sense and is grounded in truth. So the steps for implementation, and we can't shortcut these steps. You have to have, first of all, data. Connect all the data sources. So in bioprocess, that means all the data, whether it's data that resides in your electronic lab notebooks, on your paper notebooks, LIMS systems, Excels, real-time data that's from the bioreactors or downstream devices, any offline analysis that's done, offline assays or other analytic devices, SCADA historians if you have them, and also other things that like SOPs, reports that are unstructured. We need to have those sources also input into our systems so that the machine can read and get that understanding and context. And that brings us again to context. And I think I've said it before, and I'll say it a few more times during this this presentation, because it is one of the key things for good AI is to have that context. So connecting the metadata to our runs, the lineage between the different units, all the observations that today reside either offline in people's heads, in someone's notes in their top drawer. The goals of what we're trying to achieve in the run, it's also important to understand the why and what we're trying to achieve. And also incidents that happened and occurred during the run. So if we had a chiller malfunction, we had a power outage, we had an air feed that was disconnected, or we ran out of media, those incidents, it's important to document them so that there's an understanding of why this process behaved differently from another process, and learn from that. Then we have the intelligence layer. So first of all, analytics tools and dashboards so that we're able to visualize the data and understand it. It's something we discussed before, the ability to ground our understandings in the truth and the source of the data. So it's good to have that visualization. AI agents enable us to ask open-ended questions that are able to dive into the data on broad data sets. So not just showing us a graph and being able to manually overlay things on a graph, but to ask deeper questions on large data sets and get answers. And also additional augmenting capabilities like soft sensors that give us biological measurements by training on the data, predictive models that understand what the process is doing now and where it will lie in when it's complete on an online process. And on the bottom layer, something that's very important to keep in mind, governance and security. So it's important that regardless of what model you're using, what data, what platform, what you're using, is to make sure that your data privacy is secured along each and every step. So, for example, using ChatGPT not in an enterprise environment does not ensure that your data is not used to train or shared with other users. Within enterprise solutions, then you get that assurance that it's only for you, and you need to make sure that's assured both in the instance that you're using and also contractually with whoever's using that data and able to use it. The journey towards AI has 4 steps, which we'll cover. I like to look at it. It's not like a 4-step waterfall that we need to climb those 4 steps, but more as 4 steps that we do at each and every stage iteratively and build on top of them. And I'll explain further in a minute. So first of all, the stages, first of all, digitizing the data to make sure that it's queryable in an electronic format. The next is to have automation that makes sure that the context and the data is ingested automatically and then makes it AI ready. The next step is to be able to have targeted scientific questions and machine learning models that analyze the historical data to understand specific questions and validate hypothesis. And the last stage is to have deeper AI-based insights that work in the background, like we're used to ChatGPT, AI agents that understand by themselves a lot of hidden treasures in the data and reveal to outcomes. And now I'll touch into what I mean by break it into iterative chunks. So let's start with stage 1. Do I need to make sure that I have an understanding of all the data and different data points that I'm ever going to need when I'm at stage 4? The answer is no. You'll never understand everything that you need. You'll need to start with what you have and then build on top of it. So you do stage 1 with what data is accessible. It doesn't need to be perfect. It needs to be good enough. Stage 2, stage 3, stage 4, get that done as quickly as possible, get value out of it, and improve it. When you'll understand, wait, if I add this sensor, I'll get, like we understood in, for example, with the temperature sensors, then I'll get more insights. So you go back stage 1, add the sensors, and build on top of that. And these iterative chunks mean that you're constantly getting value out of the system, constantly improving the system, and not building something that will be ready in 2 years' time, but maybe not relevant. And a lot of the understandings along the way that you'll get from doing that iterative approach will bring you to a much better system in a shorter amount of time. Another key question to ask with using AI system is trust. There's a very big bias in terms of trusting a machine. It's in all our interactions with devices. Even one example is autonomous vehicles. So autonomous vehicles are available in very limited geographies. And in some cases, you see that they do have accidents, relatively a few accidents, but each accident has a very massive fallout because it's easy to forgive a human that has an error than it is to forgive a machine that runs over someone. And I think the example here of an employee that was right 85% of the time would be a model employee versus a machine that's wrong 5% of the time. We would be fixated on that 5% when it was wrong. And one of the things to understand here is it's constantly improving. That feedback loop, as we said, ChatGPT is constantly improving because of that feedback loop where it's training and improving. And the same with each and every device. So when we started using GPS 25 years ago, we didn't have traffic patterns yet. So in some cases, it gave me a route that was not as good as I knew by myself. But as it improved, it learned traffic patterns. It learned how to better navigate. And today, probably even on a route that we know, our navigation systems perform better because they know the traffic pattern in real time and can take us in a more efficient route than we would by ourselves. And we need to understand that it's not perfect, but it needs to be, the key thing is it needs to be at least as good as or better than we would do without it. There's a few, we won't dive deeply into this, but just to segment a few examples of AI in biology. So there's a few key categories. There's even more that you can expand on. The key thing to understand here is there's different categories, and for each category, there's different things that need to be done. So for drug discovery, there's a specific data sets that are relevant for it. There's specific things required for it, and they are not necessarily the same things we need for bioprocess optimization or for protein engineering. And the key is to understand what we're trying to achieve, what the best-in-class systems are in each and every area, and then we can use those. We'll go back to a few pitfalls and common things that cause AI and in general software and complex software projects to fail. So the first, the bioprocess data is scattered and not standardized. So the first pitfall is to make sure that you're organizing the data and standardizing it across your organization. And making that easy to use and preserving the context. So the context, which we touched on, the importance across this talk, it's very important to make sure that you're digitizing that context. And the key to digitizing, especially things that tend to be in someone's head, is to make it easy to document. So if you have a good place to put it, then people will document it and add it. So you'll see that good systems drive even better documentation. The third, and this is key to any project, if we define a project that's too large and complex, the probability of failure goes up in a very exponential manner. So breaking down the project into small deliverables and building on top of those is something that is key to risk reduction and make sure that our projects succeed. So starting off with a part of the process, a subset of teams, and then expanding and building on top of that is something that will increase the probability of success and lower risks and shorten timelines ultimately. And the last is unrealistic expectations. So AI is only as good as the data that it's trained on. And if we don't have data, then it won't know and won't be able to deliver the results that we want. So, for an example, if we have an organism that we have just engineered and we're running it with specific, we've only run it in specific environmental parameters and we had no variability, then an unrealistic expectation is for an AI system to tell about that organism if it's not something that's in that data set or in the literature, what is the optimal parameter for it. It's a realistic expectation would be if there's no literature. So one, if there is literature, then the AI system can take the literature and validate it. If there's no literature and it's something that's totally new, then to do what the optimal exploratory runs would be. So to do an exploratory DOE campaign to get that data so that the AI system can use that data to improve in the future. So that's something that's also key to understand and how to deploy. Lastly, I'll show just to get a glimpse and a taste of what an AI platform can look like and the few key things in bioprocess. I'll just show a very, very short demo to see that. So, just a second, and then we'll dive into the questions. So here we're looking at the bioreactor platform. So in this case, we have a campaign that's for development of a biosimilar. This campaign has, I think, about 24 runs with all the different stages for each run. So each run starts from seed train through downstream processes for that run. We can actually show the lineage. Don't be overwhelmed. There's, as I said, it's quite a lot of runs, but I'll zoom in to just show and what we're talking about. This is what I touched on when I said context and lineage between different units. So starting from upstream, harvesting, extraction, downstream processes, formulation, analysis. So having that lineage and connectivity to understand the different stages, that's what we mean by context between different units. That allows us to, for more complex questions on top of that system. So then when we go and start chatting with the data, so I have here a question that I asked the system. And in this case, since we're trying to develop, solve glycosylation in the targets here, I asked it what's controlling the glycosylation, and please search the literature for corroboration of the hypothesis. And what the system does is, first of all, run a search on all of the data that we have. In this case, we had 24 runs. And as I said, first of all, we're grounding the results in the data that we have. So the ability to visualize the data that we ran. These are our experiments that are in the system. So showing the results, that gives me the confidence that this is not an hallucination now, that it's not inventing papers that don't exist. The second aspect is it's giving me a few different process parameters that are significantly, statistically significant for the outcomes. And then it's also, again, grounding with the truth in our data. So again, not bringing and inventing data, it's ground in the data that we fed it, in this case, the data that we have, also data from literature. So if there is literature that's relevant for this organism and for this process, then we ground it also with literature support. And again, when we say ground, it means that also it gives me the link to what paper. So it's a real paper, and that paper actually makes sense in this context. And these are the aspects that are key to drive, one, trust, and to show that how strong the correlation and the results are. And in the cases where we don't have enough data to support, to be able to do a design of experiments campaign, and then get the relevant data so that we can support it better. So that's I think where we are, and we can go to questions from the audience.
Yes, thank you. Thank you, Ori. Please don't forget to put your questions in Q&A and let me check what we have so far. One second. Okay, so here's one question. What are examples of small incremental improvements that created real value without big AI?
So I think one of the things to look at is, do I always have to look for that one parameter that will give me a 2x or 3x improvement in my process? Or the other option is to do small incremental improvements week over week, run by run. And that approach, I think, provides, in a lot of cases, a much better value. And we've seen it with our customers who are doing design of experiments that are planned on a run-by-run basis. So each week or 2 weeks, depending on the process length, they do another campaign that's based on that campaign. So revalidating with that campaign the results from that campaign, and then doing another improvement. And from each and every run, they're learning and getting a small improvement, small incremental improvements. So the question is, are we going to run 1 year hoping that we hit that jackpot that will give me that 2x improvement? Or if I do a week by week improvement, each week improving by a few percent over those 52 weeks of the year, what will I reach? And in that case, usually you'll reach a much, much higher outcome because it's compounded, and each week you're compounding that incremental improvement and getting over 100% improve over that year.
Got it. Here's another question. What's the most common piece of missing context that breaks AI in bioprocessing?
So the key process.
Most common piece of missing context, because we talked about a lot about context.
Yeah. So there's quite a lot. I think the most common one,
It probably varies.
let me think about it. So there's just so many of them. So I think if we take a look, let's take a look at just upstream. So in an upstream context, I think one would be to have the offline and online measurements in the same place, so to have all the raw data correlated and contextualized. Because a lot of the times when doing those correlations, missing a lot of the time series data because it's already in the summary where you connect the offline and online. And that context is sometimes something that's key.
Here's another question regarding context. For the AI analysis and interpretation, do you assign a weighting to the context data such as observations compared to quantified data such as sensor data? So do you assign weight to the context data such as observations compared to quantified data such as sensor data?
So we understand how the data is structured. So we by analyzing the data and the variability of it, and that gives I think and then that also gives the weights and how to take it into account. And if there's no variability, for example, then it's also something that's not taken into account.
So depends on the weight.
Yeah.
Next question. What are some ways to record and store relevant data in a structured way?
So if you're say starting out, not using a system, then having structured at least a structured Excel. Unfortunately, it's what's most predominantly used, but at least have that structure and keep that structure, even if you're changing it over time. Try and at least for each time point have that structure across the teams. So not have each person have 3 different Excels just because it's easy. So that's one thing. And when you're doing those Excels, make sure that you're not just free texting everything, because it's in some cases very easy to just free text in that same cell an entire story, break it up into different columns for each thing. So if you have a goal, say my goal is yield, my goal is this, and not just have a single blob of everything that's not structured, because that makes it very hard later on to understand from that unstructured data what we're trying to achieve, what we observed, and what we got.
I also put a blog on how to structure bioprocessing data in a chat for everybody. It's on our website. It's literally called How to Structure Bioprocess Data. So Yaron, our CTO, had a webinar a couple months ago where he went very specifically on how to structure data and specifically talking about the free text and naming columns and being specific about how the measurements are captured. So for anyone who's interested, this is a good blog, and there's a webinar recording as well talking about specifics on how to structure data if you're using Excels, because it's one point where everybody starts so far. Let me see any other questions. So last question, unless anybody else asks anything additional, what kind of AI or analytics actually delivers value today in real bioprocess environments? What kind of AI?
So I think one of the things to understand is, since there's not a lot of public data sets, the important thing is to make sure that you're training on your data. So I think an AI system that is trained on your data and takes, again, the literature available, which is usually at least in our customers as we see them, it's companies usually have a much better understanding of the organism than there is in academia very, very quickly, because they run and more runs on their organism than academia, and also with a much more focused and targeted goal than academia. So a system that's relevant, I think one I can give a few examples on use cases that we've seen in our customers that provided immense value. So one is for root cause analysis, the ability to understand very, very quickly what's going on, what's driving batch to batch variability, and how to improve that. That is something that we were seeing working very, very well in bioprocess environments. Even with noisy data sets, even with all the variability in biology, it's something that we see providing immense value in bioprocessing teams.
Here's another good question. Is the AI better at identifying why something went wrong or suggesting what you should do next?
So I think there's one thing that I would say AI is much better at than humans is AI doesn't have ego and it doesn't have bias. It's only biased in the data you give it. So it is biased to the data set you're feeding it, but it's not biased to assumptions. So it will only make recommendations or conclusions based on the data that it has. Whereas in some cases, we already have the results in our mind that we want. So for example, it's just human nature, right? If I'm now analyzing Iran and I woke up today and I think it has something to do with the pH values that it's like when I'm analyzing the data, I'm already have that in the back of my mind, and I'm trying to see patterns that maybe don't exist, where the AI system will just say, okay, what's driving that result that I want to understand? Is it pH? Is it temperature? Is it something else? And it will just give an unbiased result. So that's one of the things that AI is much better at. And also, I think in terms of what should be done next, I think that's where there's, in some cases, it's a good collaboration. So depending on how much data there is in the system. So say you only have 3 runs and there's no literature on the organism you're working on. In some cases, depending on how much experience the team has. So in some cases, the team that's working has a lot of experience in their mind and will say, this is something that we need to do exploratory things for that to understand the organism. But I think the collaboration between that knowledge and an exploratory map and saying, these are the parameters that should be explored, and then have a human in the loop and say, okay, but maybe we should prioritize and do these first because this is something that we actually has more impact on the financials that we're trying to achieve. So that's something that I think is an interaction that goes well with human and AI interactions.
So really good at definitely very good at identifying what went wrong, no biases, just based on data. And in collaboration with the human, really good at suggesting what to do next.
Yeah.
One more question. What is the scale of effort to assemble sufficient data, including online, offline, goals, ELN, Chiller-broke notes, into a form from which you can train?
So here I do have a little bit of bias. I can provide case studies on what it takes in our platform. It can be very, very fast. So ranging from 2 to 4 weeks to get that for a company with quite a lot of data. We've shown it in case studies with customers. The way that we do it and the reason we can do it that fast and easily is because we built quite a lot of infrastructure around those areas. Very early on in our journey, we understood that we need to be able to take messy data, and the team here has done it also in the past in other domains. We brought that know-how into biology as well, is to take those messy data sets and very easily take with an automated tools, bring them into a structured, harmonized manner into the system.
Got it. Thank you, Ori. I think that's all for the questions. Thank you very much, Ori, and audience, for joining us today. Just a reminder, we'll be sending recording tomorrow in your inbox. And if you'd like to continue conversation and see how teams implement these practices, feel free to reply to our emails or reach out to Ori via LinkedIn. Thank you all.
Thank you very much.
See you next time. Bye.